welcome to the Explainer. Today we're going to look at the history of numbers, but honestly, we're not just going to stare at a boring timeline. Just imagine it. Humanity literally starting at level 0, right? No concept of counting whatsoever. And then slowly but surely unlocking the cheat codes to the universe. All right, let's dive right in.
So, picture this. You're living thousands of years ago in a tiny agricultural settlement. You've got a herd of cattle, and they head out to graze in this dense forest every single morning. But here's the catch. You don't have any words for numbers, no written symbols, nothing. So how on earth do you know if a calf wandered off by the time the sun sets? Well, for early humans, the answer wasn't counting like we do today. It was a really clever trick called one-to-one correspondence. Basically, you drop one pebble into a pot for every cow that leaves, and you just take one out for every cow that comes back. Boom! That right there, that was the birth of natural numbers. Now, let's look at how this builds across a seriously epic scale of time. Just think about these dates. The earliest physical evidence we have of humanity actually recording natural numbers takes us deep into the heart of Africa, literally tens of thousands of years ago. Our very first mathematicians weren't writing on paper, obviously. They were using tally marks carved straight into bone. They were tracking time and nature way, way before civilizations ever built cities or wrote down laws.
Section 1. Carving numbers in bone. So how exactly did our ancestors record this stuff? Well, you've got to consider the physical evidence itself. This is the Ashango bone. It was found near the headwaters of the Nile River, and it dates all the way back to around 20,000 BCE. But here is the crazy part. Look really closely at the grouping of the tallies in one of the columns. You've got 11, 13, 17, and 19. Do those look familiar? Yep, those are exactly the prime numbers between 10 and 20. I mean, there is no way this was just random scratching. It proves that the abstract concept of a number, and specifically prime numbers, is tens of thousands of years old. Honestly, the level of abstract thinking our ancestors had is just absolutely awe-inspiring. Section 2. The Revolution of Zero.
So for millennia, humanity was leveling up just using these natural counting numbers. But think about this. What happens if you have, say, 5 apples, and you give all 5 of them away? Well, for thousands of years, you literally didn't have a number to represent that state. You just had a void, right? A lack of apples. And this brilliantly illustrates where our next massive leap came from. It actually didn't start in a math ledger at all. It started in philosophy. Over in ancient India, thinkers deeply revered this state of emptiness. They called it Śhūnya. Because they already had the conceptual framework to embrace nothingness as this really profound philosophical idea, it eventually crystallized into the mathematical concept of Śhūnya, or zero. The void was finally getting its own symbol. But, a symbol is really just a mark until it has some hard and fast rules. And in the year 628 CE, this brilliant Indian mathematician named Brahmagupta formally transformed that void into a fully operational mathematical tool. He explicitly defined zero and laid down the absolute fundamental laws of arithmetic that we still use every single day. I mean, his 1,300-year-old rules laid out perfectly. When zero is added or subtracted, the number stays exactly the same. But when multiplied by zero, the result is zero. Just like that, the engine of modern math was officially powered up.
Section 3. Debts, fortunes, and integers. Now, Brahmagupta didn't stop there. He posed this incredible challenge. Okay, so we know 5 minus 5 is 0, right? But what in the world is 3 minus 5?
To figure this out, Brahmagupta actually grounded his math in the everyday reality of commerce and daily life. He recognized 2 distinct states. You have fortunes, or dana, which are basically your positive assets, your money in the bank, and then you have debts, or rina, which are your negative numbers. By making that jump to the left side of 0 on the number line to represent debt, Brahmagupta formally introduced negative integers to the world. He basically took this super abstract math and brilliantly tied it straight to relatable human reality. A total game changer.
Section 4. The magic cyclic numbers.
Okay, so we've built out our number line, right? We've got positive numbers, negative numbers, and 0. The next level up? Unlocking rational numbers, fractions. And hidden right inside them is a literal magic trick. Seriously, take the fraction 1/7. If you divide 1 by 7, you get this repeating decimal block, 142,857. And it just loops forever. At first glance, it just looks like a totally random string of digits. But watch really closely what happens when we actually start multiplying this specific block of numbers. Just look at this. When you multiply 142,857 by 2, 3, 4, 5, or 6, the exact same digits appear. They literally just shift around in a cyclic swirl. Multiply by 2, and it becomes 285,714. Multiply by 3, and boom, it's 428,571. By 4, it's 571,428. By 5, you get 714,285. And by 6, 857,142. This is what we call a cyclic number. And it's so cool because it proves that math isn't just some random set of rules we made up. It actually possesses this beautiful built-in internal rhythm.
Section 5. The irrationality of root 2.
Right up to this point, ancient mathematicians were pretty convinced that all numbers could be neatly expressed as beautiful, predictable fractions, or those repeating patterns we just looked at. But buckle up, because the universe is about to break. We're about to introduce a shape that completely shatters the pristine rules of rational numbers. But hey, before we break the rule, let's make sure we firmly establish what it is. A rational number is basically any number that can be expressed as p over q, where p and q are integers, they share absolutely no common factors, and q isn't 0. Keep that in the back of your mind because a whole lot of irrational chaos is about to completely contradict it. Imagine a really simple square, right? Each side is exactly 1 unit long. Now, if you draw a diagonal line straight across that square, the good old Pythagorean theorem tells us that the length of that diagonal is the square root of 2. Well, around 400 BCE, this mathematician named Hippasus came along and posed a genuinely dangerous paradox. He asked, can the square root of 2 actually be written as a clean, simple fraction? To figure this out, Hippasus used this brilliant trick called proof by contradiction. Let's walk through it. Step 1. Let's just assume root 2 is a perfectly simplified fraction, p over q. Step 2, we square both sides. So now 2 equals p squared over q squared. Step 3, multiply by q squared, which gives us 2q squared equals p squared. And here is where the absolute disaster strikes. Because p squared is equal to 2 times an integer, mathematically, p literally has to be an even number. And if p is even and q is also even, well, they share a common factor of 2. That completely breaks our simplified fraction rule from earlier. The stunning realization here was that some numbers, irrational numbers, have endless, non-repeating decimals that can never, ever be written as fractions. Mind blown, right?
Section 6. Madhava's Infinite Pi Series.
And that brings us to what I like to call the ultimate final boss of the number universe, pi. We all know the ratio of a circle's circumference to its diameter is famously irrational. For literal centuries, mathematicians were losing their minds trying to find the perfect fraction for pi, and they all failed. Actually, it wasn't until the 14th century that this absolute genius from the Kerala School of Mathematics finally cracked its exact formula. His name was Madhava of Sangamagrama. He realized something incredible. Because pi is irrational, no single fraction is ever going to give you a perfect formula. To express a truly irrational number exactly, you can't just use one fraction. You have to use an infinite sum. To find exact pi, you literally have to add and subtract fractions infinitely, forever. It is like this swirling, endless galaxy of mathematics.
So, from tally marks carved into 35,000-year-old bones, to the profound philosophical invention of zero, all the way to the mind-bending reality of infinite series, we've really seen how humanity leveled up its understanding of the universe. But, going through all this leaves us with one final, pretty provocative thought. If the real number line is completely unbroken, if it's continuously packed with this endless sea of infinite fractions and chaotic, irrational decimals that just go on forever without ever repeating, where does the rabbit hole actually end? And what bizarre new numbers are out there just waiting for us to discover them? Think about that the next time you're just counting your change.